Welcome back, everyone, to our ongoing deep dive series on the Online Encyclopedia of Integer Sequences. The OEIS is just such a fantastic resource for anyone studying number theory.
Absolutely. And today we're zooming in on one specific entry, A000199.
A000199.
Right.
And this one deals with coefficients from one of Ramanujan's Mach theta functions, FQ.
That's the one. Specifically, the coefficients of Q raised to the power 2n1 in the series expansion of FQ.
Ramanujan's Mach theta functions. They always sound so, well, mysterious. Why this sequence? What makes it stand out for a deep dive?
Well, it's a great question. This sequence, A000199, it's sort of a gateway. It lets us explore the history and the really quite peculiar nature of these Mach theta functions themselves, and it connects to, some surprisingly broad areas of math and even physics. So our goal today is really to trace that story. We'll be looking at how Mach theta functions were defined, or maybe not defined initially,
Right.
how they relate to modular forms, and some specific things about this function FQ.
Okay, sounds fascinating. So the logical place to start is, I guess, with Ramanujan himself. How did these things first appear?
It all goes back to Srinivasa Ramanujan's very last letter to G.H. Hardy. This was in 1920, really just months before he sadly passed away.
Wow.
And in this letter, he introduced these unusual Q series. He called them Mach theta functions.
But he didn't give a strict mathematical definition, did he? I remember hearing it was more descriptive.
Exactly. It was quite informal, quite intuitive. He talked about them being functions written as Eulerian series. These power series often connected to things like partitions. And they had these exponential singularities all over the unit circle. The key thing, though, was their asymptotic behavior near these points.
How so?
He said they sort of closed his word as neatly as ordinary theta functions did when you approach those singularities. But crucially, they weren't just an ordinary theta function plus some, simple bounded function.
Okay. So they mimic theta functions in some way, but were fundamentally something else. That's the Mach part.
That's precisely the idea. They had this theta-like property asymptotically, but weren't the real deal, so to speak. He listed 17 examples in that letter.
17.
Yeah. And his lost notebook, discovered later, had even more. He also gave them an order, like order 3, order 5, order 7.
And does that order mean something specific now?
It does now, yes. It took a while, but it's now understood to be related to things like the conductor of a related character. It's like a classification system.
So this lack of a formal definition must have created some work for mathematicians, trying to figure out what he really meant.
Absolutely. For decades, people like Watson, Andrews, Selberg, they really dug into this. They proved many of Ramanujan's claims, found new identities, a lot of which, it turned out later, Ramanujan had already jotted down in his lost notebook.
Incredible. And Watson, you mentioned him. He made a key step with the order 3 functions.
Yes, that was quite significant. Back in 1936, Watson showed that these order 3 Mach theta functions behaved under modular transformations, almost like weight 12 modular forms. Almost. The difference was the specific error terms. He even managed to express these errors as explicit integrals. It was a big step towards pinning down their structure.
Okay, that sets the scene nicely. Now let's zero in on the star of A000199, the function FQ. Can you remind us of its series expansion?
Sure. Ramanujan defined it as FQ equals 1 plus q divided by 1 plus q squared plus q to the 4th divided by 1 plus q squared times 1 plus q squared, and so on. It's one of his third-order examples.
And A000199 just lists the coefficients of q to the 2n1, so the odd powers of q in that series.
Exactly that. It pulls out that specific thread. But to really understand FQ and functions like it, we need the modern perspective, which connects them tightly to modular forms.
Right, you mentioned modular forms, and also harmonic mass forms. How do they fit in?
So the modern definition basically says a Mach modular form is the holomorphic part of something called a harmonic weak mass form.
Holomorphic part. So there's a non-holomorphic part too.
That's right. These mass forms are, they're non-holomorphic functions, but they still have nice transformation properties, similar to modular forms, and they satisfy a certain differential equation. The nice part, the holomorphic bit, that's the Mach modular form.
Okay, I think I follow.
A really huge step forward came in 2001. Sanders Wiegers made this incredible connection. He showed how Ramanujan's Mach theta functions were related to non-holomorphic modular forms, specifically involving things called Lurch sums and indefinite theta series.
That sounds like it really clarified things.
Oh, tremendously. It put them on a much firmer footing, linking them into the established theory. It turned out Ramanujan's functions, maybe with a small tweak like multiplying by a power of q or adding a constant, were basically the first known examples of these mock modular forms.
Okay. And there's this idea of a shadow as well. What's that about?
Yeah, the shadow is important. Every mock modular form has an associated shadow. This shadow is a proper holomorphic modular form, typically of weight 2k, where a is the weight of the mock modular form.
So the mock form isn't quite modular, but it casts a modular shadow.
That's a great way to put it. It captures the way the mock form fails to be truly modular. It's like the deviation from perfect modularity is itself modular. And interestingly, different mock theta functions can actually share the same shadow.
Huh. So they can look different, but have the same underlying modular imperfection.
Exactly. Zagier later refined things, defining a mock theta function in terms of a weight 12 mock modular form whose shadow is a specific kind of theta series. It provides a very precise characterization.
Okay. Now, Ramanujan also looked at how these functions behave near the edge of the unit disk, their asymptotics. What about FQ?
Right. Watson studied this for FQ too, especially near roots of unity. He found connections between FQ and another Q series he called BQ.
BQ, what does that look like?
Well, Watson wrote it as an infinite product, 1Q, 1Q3, 1Q5, multiplied by another series, 1, 2Q plus 2Q4, 2Q9 plus.
That second part looks familiar, like a theta function.
It is indeed related to a theta function. Actually, BQ has a cleaner infinite product form. It's QQ infinity divided by QQ infinity squared using the Q-Pochhammer notation.
Wow.
And more recently, Folsom, Ono, and Rhodes got a very precise result about the limit of FQ minus 1K times BQ as Q approaches a primitive root of unity, zeta, of even order 2K.
And what's the limit?
They showed it equals minus 4 times a specific sum involving terms like 1 plus zeta up to 1 plus zeta in the numerator and 1 zeta up to 1 zeta 2 1 in the denominator, all times zeta and plus 1. It's quite a complex formula, but it nails down the behavior at these critical points.
It really shows how far the analysis has come from Ramanujan's initial intuition. Now, I was really surprised to see a connection to topology, not theory.
Yes, this is one of the most, unexpected and beautiful connections. It turns out FQ is deeply linked to something called the colored-Jones polynomial.
The Jones polynomial
Sure.
from not theory. That one.
Specifically for torus knots, like the left-handed trefoil knot, T23, that same limit value we just discussed, the limit of FQ minus 1 kappa BQ as Q approaches certain roots of unity, is directly related to the n-colored Jones polynomial of the trefoil knot.
Wow. That's quite a connection. Number theory coefficients showing up in knot invariants.
It really is. It points to some very deep, maybe still not fully understood connections between these fields. It's an active research area.
And the connections don't stop there, right?
Yeah.
Our sources mentioned black hole entropy. That seems even further afield.
It does, but yes, this is probably the most dramatic modern application. Mock modular forms, including those related to FQ, have become really important tools in string theory, particularly for calculating the entropy of certain types of black holes.
Didn't Freeman Dyson predict something like this?
He famously did. He speculated that physicists studying superstrings would eventually need mock theta functions, and it seems he was right.
So how does it work? How does a Q series relate to black hole entropy?
Well, very broadly, black hole entropy is related to counting the microscopic quantum states that correspond to the black hole's macroscopic properties. In string theory, this counting often involves partition functions.
Oh.
And these partition functions, especially in more complex scenarios beyond the simplest cases, turn out not to be nice modular forms, but often mock modular forms. Their asymptotic growth, how quickly the number of states grows, is calculated using methods similar to the Hardy-Ramanujan circle method originally used for integer partitions, PAM.
So Ramanujan's original work on partitions kind of paved the way.
Absolutely. His work on PN was foundational. For simple string theory setups, the state counting might involve inverses of things like the Dedekind eta function, which is modular. But for more sophisticated black holes, the counting functions are often mock modular. Their coefficients tell you the number of states and thus the entropy.
That is genuinely mind-blowing that these functions Ramanujan described almost cryptically in 1920 are now helping us understand black holes.
It's a testament to the depth of his intuition and the surprising unity of mathematics and physics. Dyson's prediction really hit the mark.
So wrapping up our deep dive on A000199, it's really been a journey. From Ramanujan's letter, through the struggle to define these functions, to modular forms, not theory, and black hole physics.
It really highlights how a single sequence in the OEIS can open up such a rich and interconnected landscape. FQ started as a mystery, a mock theta function, but it's become a key player in modern mathematics and theoretical physics.
For the number theory students listening, what's the main message you'd want them to take from this specific exploration?
I think it's the unexpected relevance, how something seemingly abstract, like the coefficients of a Q series, can ripple outwards and connect to fundamental questions in topology or even cosmology. It shows the power of pursuing mathematical curiosity. Ramanujan's work continues to resonate in ways he likely never imagined.
It certainly underscores the value of resources like the OEIS. It makes you wonder, doesn't it? What other connections, what other profound applications are just sitting there in those sequences waiting to be discovered? Thank you. This has been incredibly insightful.